Aldous,
You were seeing, I had forgotten you had seen my screen.
oh, yeah. Aldous, does that sound good?
Yes, yes.
Okay,
Perfect, of course.
great. I'll do an introduction. Okay, so good afternoon, everyone. For those who don't know me, my name is Matt Ricci, and I'm a postdoc at the Data Science Initiative. I'd like to welcome you to another Data Wednesday, Thursday edition of Data Wednesday. So far we've had a great lineup of speakers this year, and that's going to continue next week when the DSI and CCMB welcome geneticist Sriram Sankara-Raman of the UCLA. Next semester, we're also excited to invite Robert Grice, the applied topologist from UPenn, and Renato Mirolo, the physicist from Boston University. You can learn more about all these events on the DSI and CCMB websites. But today, we're very lucky to have with us Marta Gonzalez, who is Associate Professor of City and Regional Planning and Civil and Environmental Engineering at Berkeley, as well as a physics research faculty member at the Lawrence Berkeley National Laboratory. A scholar of complex systems and network science, Professor Gonzalez develops numerical models and computational tools to better characterize and understand human interactions in built and natural environments. Today, her talk is entitled Cases of Study in Computational Urban Science. So would you please join me in welcoming Marta Gonzalez.
Hello, everyone. Happy to be here sharing my work in a very broad set of researchers in data science. My focus is going to be in urban systems, with the caveat that the field is changing because we have novel data sources into the field. And then, of course, let me start what was before the novelty. And in urban planning, we want to estimate what is the demand, how people need infrastructures, and the typical situation is traffic. But it also applies when you are not moving in a given city, you are normally in buildings, and then you're also, we need the space, where the jobs are, where the home residential areas are. Then it's a field that has been studied a long time, and the usual way is travel diaries. They would ask people, for example, in the Boston area, greater Boston area, we had 3.5 million people living there. They would interview 10,000 households to ask them what they do in a day, the entire day, all the trips. Then from only that 1%, they need to synthesize the entire population to generate the activities. And some of the transportation problem is route planning. So it's not entirely random or surprising. It's a problem of capacity versus demand. So when cities go completely not planned, things happen, and that should not be surprising. Then that was the field. It was agent-based models, econometric models to do this activity generator choices, very hard to calibrate. When a few already 10 years ago, especially in transportation planning, the ability to have geolocated information, that our data became digital. I like to say we gave up our privacy with the goal of have access to information all the time. So the more we connected we are leaving traces. Typical data sets are smartphones. It can be surveys or just apps, or literally a mobile phone, that is the antenna usage, your bill, the mobile phone provider have it. Then it's different location-based service, a smartphone, and any phone like by the phone providers, social media data, even credit card transactions. Can we use those traces to do the same that the other estimates were doing? The answer is yes, we can, but what do we need? We need representative sample of the entire population. If you are not using the service, you still need to be there. Then we need to have representatives going from users to total population, and it needs to be independent that when you use it. Sometimes people is tweeting a lot because something happened that the activity is not the same as the presence. Then we need to have complete location of individuals. That means when they are not using the app. The approach I'm going to present to you how we did develop that is a collection of years of work, and the field is called Human Mobility Patterns, Mobility Science, and it brings together any discipline, but what we have in common is complex systems. There in Quanta magazine, you can see complexity science or emergence. This is a field that study open systems that are not deterministic, that you cannot do all the rules at the microscopic level, but you can see the emergence of patterns. Flocks of birds in the sky, or traffic and synchronization. There are many fields and ways or techniques to study complex systems. I focus in urban systems as a complex system, and that is the type of approach we do. Which this means is that we're going to be seeing the emergence in the pattern of mobility. You will see them in detail later, like visited locations per day, a stay of the locations, without knowing why they're doing that. For some people, that is not as interesting as a behavior, but for others, the applications are there. So what we're going to be doing is the emergent patterns of human mobility using data. If the model is good, it doesn't matter where you apply it, it should withstand. That's what we're going to be navigating right now. The first data, one of the data sets I'm going to be doing, this is perfect opportunity to do it, is 800 students self-collected data with smartphones. A former postdoc colleague of mine, Sune Lehmann from Sensible DTU in Denmark, got this grant, gave very cool smartphones to Danish students, and he could track everything. Wi-Fi, Bluetooth, GPS, they allowed to do that. And then it was a perfect reality mining experiment inspired by the Sandy Penland's reality mining experiment that he did with Nokia phones. He's from Media Lab. Then depression, sleep routine, etc. We're going to be focusing on the boring part of where they are every time. Here is, they go over the planet because it's 2 years. Even if I spend the entire talk talking about the model, probably it's not going to be as clear as you're reading the paper. Then I'm going to tell you the bites, the important things of the model. And that is the patterns, how we develop it. We got all the users. Again, it can be applied to any geolocated data, and our goal is to complete the trajectory. That's why we need the model. Of course, we're going to check the properties of the model with active users, like the Sensible DTU, where you have them all the time. Then we develop the model and then treat it, use it when the users are sparse. I'm going to show you the details. Then the big picture is, the first thing we did is circadian rhythm. Right here, what is the probability that at a time t, a non-commuter have a trip? PD is departure, probability of departure at a given time of the day. How we do it? The simplest possible way, adding everybody together. Then we have individual parameters. Even if this is circadian, everybody, this is number of weekly departures. This is a temporal probability of everybody, but then NW multiplies the PD because some people, we see them departing many times their house, some of us don't. This is not in COVID. COVID required other studies. But then you can see this heterogeneity in at what time is the circadian rhythm, how many typical departures you have, still easy to measure. Then they come to rates, and it's going to control the probability that when you are somewhere, so if you're at home, you decided to depart, yes or not. And then if you are going to do a departure, you need to see if it's an exploration, meaning you're going to go to a new location you never visited before, or you are going to go to a fixed location that you have been there before. This can be called this is the case you stay at home. This is the case that you choose to move, and then it's an exploration or a new visited location. Then once you are in a location, the situation is you stay there at every time step, every 10 minutes, you stay in that other type of location, or you move. And if you move, again, you need to decide if you're going to go to some other places or you go back home. That would be this. Then what controls the difference between you and me is how long I stay in every location and my decision to go back home or not. They are heterogeneity. Some people stay longer in the flexible activities. Some people visit many flexible activities per day. That is controlled by beta 1, beta 2. And this one here is the rate between explorations and preferential return. That was an entire model that was called the exploration and preferential return model by Barabasi's group. That is something that is a universal, we call it a pattern that we also put in this model. Notice the solid line is a distribution. This is data. Every time you measure that, it appears this with different gammas and rho. The next the final difficult thing is when you're doing an exploration, there is no machine learning model that is going to guess where I'm going if it's a place I never saw the person in. You know, you cannot infer a location or predict a location you never had your user there. You have to be magic, right? Well, the way we do that is simple. It's the so-called gravity model, radiation model. That means simple because we have maps. Then in the map we have point of interest. And it turns out that there are laws. If I'm going to go in my flexible location, I have the point of interest of the map, likely I'm going to go to the closest commercial area. It comes all summarizing this PK speed ranking. So these two, C and D, came from previous papers. And we basically put together beta 1 and the rho. I myself was a student and postdoc of the previous type of papers, but this is a community effort. Then let's test it. In one of the DTU, Danish students, we can see, this is just a snapshot, the longitude of where the person is and the movement. Then here in a zoom, you see, overall, sometimes you don't accurately predict where the person is going to be. Not if you're staying. If you're staying all the time in your house, the prediction is perfect. I'm talking here, when you move, what's the likelihood? I'm going to predict the person well. Basically, it depends on your preferential returns, but it goes between 58 to 79. If you see this with the computer science hat, oh, it's not so good, right? However, it's very good for the urban planners, and that is what we need. These models that is not about predicting the individual, is finding the patterns such that we can generate our model with the betas and the NW and all the rules of the distribution, preferential return, and the decisions, and we can predict number of visited location of one person per day over a year. Sometimes there are some days that you visited A, some others you visited 1, etc. This person that we're tracking here is a special meaning because it's my first PhD student. He tracked himself and he donated the data. Another student doing the work was doing the models. He's not author, it's Jameson Toole, the student that we were tracking here. But it can apply, you will see, for everybody and beyond these smartphone data users. So number of locations per day, how long you stay in every location, what is the ranking? So location 1 is the fraction of time I'm seeing in my home, in my work, and in others, I only see 1 over my entire number of locations, and the distance. Of course, if we have the visited location of people, the distance distribution is mostly dominated by home work type of activity. I show you the schema with a non-commuter, and this is a commuter, the student, it was a PhD student. Here is the histogram. Just by having the rate and that we have 24 hours of the day, we reproduce these individual mobility networks, the types that are the so-called motifs, another paper on motifs. So that is the flavor of these models. The data sets, it can be any, you need to determine the location. In the case of triangulated antennas, you have the locations are pretty good. They seem at the census tract resolution. In the case of LBS, location-based services, you need to do parsing trajectories because you can see the person in long lat, several long lat that is home or work. You do a DB scan clustering to determine the so-called state regions or locations. After you do that, then you lose resolution and you have somehow a resolution of about 200 to 400 meters, and that is what these models are good for. The trips that occur between locations among blocks of your city, not within buildings, that's other type of behavior. And the time resolution is every 10 minutes. Here in the left-hand side, the distributions of the sensible DTU users, the active users, and in the right-hand side, triangulated data from phone data. AirSage is the company that provided the phone data for that. The distributions are log normals. They are so common in data. They are different. This is only a student. This is entire population of Boston. They are not the same. What we do is we calibrate, is the same model. We calibrate the rates with the users we have from the given city. The right distributions are cleaner because we had 200,000 active users, 2 million mobile phone users, and in DTU we only have 100. But the idea is the model and the patterns. Here is an example, and here the power is that we have a person, a user like this one that only have 30 locations or so, but we saw the a big yellow mean the person was there many times. We saw this person only in 3 locations repeatedly with a few calls. But then we could say the visited location, we could generate explorations with different scenarios of this person. It can be a beta 1, beta 2 type of agent, or a beta 1, beta 3 with other values. They are different type of behavior taken from the distribution of the previous slide. Here I'm showing only 30,000 people for visualization purposes, but we could measure all the population older than 16-year-old in the Boston area. After we did that type of model, we can use it everywhere, all the time in many applications. The first things before I start using it in many things, what we did is validation. One way, similar to my first slide, traffic models. You can count cars. That has been the paramount way to validate your demand models. This is the CDR, is called detailed records, our results, and this is the transportation planning packet. I forgot what the C means, but this is a standard flows measured with cars. Intertown is easier than intratown is easier than intertown. So basically, take-home message, depending on your resolution, these ODs are harder or easier to validate. If you have many small blocks, it's very hard to validate this heterogeneous distribution. But we with phone data have our life much easier to calibrate ODs. ODs is origin destination flows. Because other people with 1% of the population, how could generate ODs? Then it really, I would say, revolutionized the way transportation planning is done. And then it comes the vision, how this is help us. This is a vision of Polpi Center, ideally because the streets are not used uniformly, but now we know where the people come from. You can target driver sources to optimize traffic. And here comes the ceiling. If the people take your recommendation, like go in the bike, alter your route, take the transit, if they would take the recommendation, then you can really target good reduction of traffic. And then the bottleneck is human adoption, but notice that in Sao Paulo, in some cities in China, and in Mexico City, they would do this for plate number. 1% of the cars ending a number cannot drive. That is not to work because it's uniform selection of the driver sources. You need to do target selection of the driver sources. A question I receive is, how representative are all the different socioeconomic statuses? Here we have from 1 to 5 is the label they put according to the economic status. In Bogota, for example, that have a lot of people in poverty. Here we have population. So 1 to 3 are the poor and middle class, and then richer in the right-hand side. Then what we do in expansion factor is the ratio between a population you are simulating versus the users. Then we go expansion factor of about per source. Expansion factor of 23 means you have 23 people simulated per 1 phone user. And of course, in the richer sector, mostly everybody have a phone. But we take into account that diversity. In short, is everywhere the way people is accessing information, even more than the computing, is their phones. So representativity would not be the big problem. And then remember, it's not only about knowing your travel time, it's knowing who used that. Every time you see a street, you can validate our travel times, but you can also know who is driving from there. Then the example, one example is alternative routing. The details of the method is in this paper here 4 years ago. But the big aspect is, because we know all the ODs, we can alternate how the routes. This lambda 0 is a user equilibrium. It's what your Google map gives you. But we know how many people accumulating in this street would generate traffic. Then you can alter it a little bit, penalizing the cost because this create traffic. In few words, even if the shortest path from here to here for a person, the user equilibrium or individual optimal would be this street, some people we need to distribute far away. What it means? The net benefit from them is negative, but notice the asymmetry. A few sacrifice and the overall system reach the social optimum. When we are in the tragedy of the common, you have limited resources and we need to distribute in such a way that some of them sacrifice. And that is the key component that we would like to start learning. What we thought is that a way to apply this technology where people is willing to sacrifice is when the Olympic Games come to your house. Then we tested this in the Rio Olympics. We needed to add other information that we got from the city, particularly where the hotel venues and the schedule of the games is, and the supply of hotels and tourist accommodations. Then data fusion at its best, we put everything together for those, I forgot the name of the famous, I'm getting old, but they are the famous stadium with the soccer goals, Copacabana, no, Copacabana is other thing. Maracanã, the famous Rio stadium. Anyway, we were here, go with me to Rio, and then we know in the months of the Olympic, how many where the games were, and how in which venue and how many people it would be going there. We had the Olympic game line, and then at the end of the day, what we did is this rerouting for the commuters. And then the result, the type of result is this, it was not 18%, but 10% better by targeting what? Origin to destination at a given time of the day with the added demand. To where we target them, not to the streets, it was too much traffic at the time, we target the users that needed to be going into the transit. The commuters that usually would drive, we target them for these months, you would go into the transit. And these type of things, there are a lot of industry and jobs in events management. But now with the new data sources, it's an example that it has been changed, the industry. That's why you have a Sidewalk Labs, a spin-off of Google, is all about the future cities. Now come with me to Mexico City. I want to do one more piece of information that is, let's go and do something different. That is learning about the why. What is it that they are doing, who they are, what's their money. So only location has a ceiling. And for that, I mentioned in my slides, we have credit card transactions. In Mexico City, we had 250, well, about 1 million debit and credit card users. Among those, 10% or so, we had phone data. In the contract of the phone data, you have age, gender, zip code. And then let's learn from that, combining these two data together. As usual, you may be already realizing I like simple metrics first. I complicate it if needed. Then one metric that has been nicely studied to do a dynamic network or to characterize network. Forget the dynamic network. To characterize network, a good metric is the diversity. It basically measures the channel entropy of the distribution of the weights. Then Pij is the different weight between node I and node J. And then if you add this, it can be uniform or it can be not uniform, is the entropy. Then this measures the divided by the total number of connections, is K, of a given node. Then you can do the diversity of the weights depending where you go, or the diversity of the ways depending who you call. And another metric that has been very handy to characterize mobility, you measure the average location weighted by the visit. That's why some are little and some are big. Then you do the center of mass of your location. And then you calculate the radius between that center of mass and all your visited locations. What that gives you is the radius within which each individual is most likely to be found. It doesn't get more simpler than that, and these quantities are powerful to measure patterns at the individual level. Then we went into the credit card transactions, and then surprise, surprise, we all spend, it doesn't matter the income, the age, or the gender. This is the frequency of the transaction, and this is the label. Most of us, if you see the top 3 or 5, is grocery, eating, tolls, computer networking, food service stations. What are we doing there is we spend, based on our money, most of the time eating, moving, and communicating. Very human, right? Then this, to do patterns and extract computational, this was harder to find the difference between a person and another. Then we apply the Sekitura algorithm, that is not the amount, not the frequency, but the sequence of the events. And then everybody had their user 1, their sequence, user 2, their sequence. And then we measure the Jacquard index, which is the intersection versus the union among users. And with that, we had per user the set of transactions similar to the motive, but it came from the data alone, not movement, just transactions. The beautiful thing is when you connect the people that have Jacquard index in the set of transactions high, nicely communities appear. We had 5 communities that were identified. Communities is a set of nodes that are more similar, have more links than to the outside. And we have this typical when you're doing clustering, this big community that was the average. We could not level any, it must be something interesting there, but we could not capture it. Then let's see these communities from the data, which is a behavioral thing. The first one was the commuters. Then the core transaction is toll, it goes to restaurant. Then here you cannot only have mobility, you have activities now. And we check, interpret. We don't use that in the data. We interpret the result of this user because we had phone data. We show that this cluster that came just from the transactions, that number of people have higher expenditure, live far from the city center, they have larger radius of gyration, and lower social diversity. That is based on the diversity and RG that I explained before. Then the next one was the housemakers. They have mostly female, a little bit older age, sadly less expenditure, that must mean less income, and the core transaction is groceries. This is Mexico City. Then we can even see the difference between women, let's say, in Mexico and California, but it's a behavioral thing of how you spend your transactions. And other aspect, oops. The diners have core transaction, restaurants, internet, a lot of mobility diversity, and more expenditure. The youth is just young population, have no car, so super young, have no car. That is the most thing. Radius of gyration, because you have no car, likely smaller. And finally, the high techs, they also were younger, but they have as a core transaction the internet services. That's the thing. We would love to see more the dollar signs, take into account the difference in expenditure and where they are, the use of space. So when we check where they are in the map, these maps, I'm not claiming, were very clear to me. They're almost surreal. This was to referee reply. But then when we see where they are, we saw some differences. Some people is most likely, this is a residual activity that is telling you if that presence of people is more than by chance. So we know that everybody is more people in downtown. So this residual activity tries to take into account the normalization and the fact that everybody follows the density of population. But we can see, for example, The commuters live in the suburbs, the high-tech users live in downtown. And we need more analysis to, and then the housemakers and also where more less income live in this part, northeast. We would like to, of course, apply the method to other label data. This is temporal label data. You can do it for a point of interest, for example, type of point of interest. Study this in several cities. What I would like to say, you may be scared, and I would be if I would be in the audience, why some researchers are having all this data? Yes, the companies have it. Notice that this was funded because it was a research needed to do outside the companies, and it was funded by foundations, UN Foundation, Bill and Melinda Gates Foundation, because it turns out that the passively collected data is giving us information in places no survey is happening. Then it was the way to know a special aspect of the economy and the situation of women and girls. Then we have the paper that was 2018 with all the users, and we did a particular chapter of this compendium with the lens of women and girls. Girls, we don't know, mostly women. Then the final piece, my last piece of information, is where I am spending a lot of my time, because it seems that to reduce emissions, we are going into electric cars. Mostly in Europe, this is happening. I have one grant by ENGIE, the power grid of the French power grid. So I can tell you some stories about what's going on with the electric cars and what would be the ceiling. As usual, I first found the data to be able to do the research. Not always I'm reaching data, only 15,000 vehicles. So I told you before I had millions of users, 100,000. I only had 15,000 electric cars moving around in the charging station. Then they would arrive, depart, and charge. So everything is mobility. In this time is not what you buy, nor where you move, is how much you charge. We also have the zip code and unique driver identifier. And here is the problem. This is the one simple charging station that have 450 vehicles charging in there on average daily. Look at the peak in the power demand. So at 9 a.m., boom, high. You know that in the power grid, they need that mostly have a good forecast and continuous demand. Of course, this is not a problem yet because less than 1% of the cars are electric in San Francisco. In the Bay Area, all this work was in the Bay Area. But this is going to be a problem and a big ceiling for the EV adoption. Then the first things we did is we wanted to start doing a scenario analysis of everybody, not the 15,000 we have. Then we did, what is the probability that somebody have an EV given the income and the distance of travel? Then we decompose this as the probability of having an EV given this, simplify, no? The probability of having an EV if you have a given income, the probability of having an EV if you have a given distance of travel in your commute, and the number of EVs. In the Bay Area, 0.62%. All these two we could have because you have the income based on the home, and the distance the EV travels, it comes from another source. So we had our own 15,000 EVs. So with these probabilities, we assigned EV usage to our phone users. So this is a model, but then the nice thing, this is simulated EVs. This is a car vehicle rebate program in which if you find an EV, you apply for this to get the tax benefits in the Obama era. Hopefully now we're going to see more of this EV and solar incentive. It works well. So it has to do with income. And if you see this here in the Silicon Valley, and you know, the most EVs per zip code we have is 300. There are very few yet, but it's an important optimization problem we need to take into account. The story is, this is a charging station. This is the amount of time you're in a given place. We cannot have this first come, first served. Based on the current demand, we would shift when to charge to minimize the peak. It's a mixed integral linear program. Every time we use optimization, we use Gurobi. And the important aspect is the demand based on the data. And these shifts are the shift, blue is the ones that are now having to depart later. And red, it means that you need to arrive earlier or later. So your time of charging is going to change based on this. This is assuming that you have the technology that you plug in your car and it starts charging, like the water when you open it. Here are the results shading the peak. If we have this flexibility in departures and arrival of 60 minutes, we have this. If we can have something else that you can move the cars and you can charge and do this without affecting the driver, but in your parking lots, you can manage the demand through the entire stay time, then you have a considerable thing. Then we need to change the technology of how the charging stations work. Most likely it's going to happen people driving around the cars, like happened with the bikes. You can bike somewhere and everybody leave the bikes near the universities and you see the little trucks taking the bikes back to the residential areas. When we have autonomous cars, they could rebalance themselves. So we don't know what is implementation, but as it is right now, it needs to happen. The simple things need to be solved to have more EVs, to even dream with autonomous cars. We inspected how these changes in the departure and arrival would change the travel time due to traffic, because remember, I'm the expert in traffic in our simulations, then it was a byproduct. Some people would benefit because we are letting them not travel in the peak. You save the peak demand and the traffic demand, then we could have benefiting commuters. Some of them would again sacrifice, but the benefit in commuting in this time is better. And the monetary saving, because the tariffs change, the power grid penalized if you go in the peak. It would be a little less than $2,000, but listen, $2,000 per month, 450 people. If you make the division, it's a coffee per day. Would you change your schedule for a coffee per day? Probably not. To have a game in which you may win $2,000 competing with 450 people? Maybe yes. But you know, the carrot or the stick, we don't know exactly when people is going to accept that recommendation. It brings us back into the adoption trends. What people would do belongs to computational social science. We have seen that this adoption of new things has been there forever. TVs, color TV, phone data, tablets. Now is EV, electric cars. The data has allowed us to see how this is going to affect demand. We need more and more work on adoption of innovations in the social network. Then that's what in this point is what I want to say. Computational social science need to go closer to, urban informatics need to go hand in hand with computational social sciences. Overall, now I'm wrapping up. What this work is about, or my dream, my mission is doing policies informed by science and engineering. The demand optimization, that is engineering, the science is the patterns. But at the end of the day, what we want to do is simplify, understand, and inform policies. We benefit from crowdsourced data and all data available. Open source government is necessary. Our techniques, everybody welcome. Data science, I guess that's why I'm here invited today. The applications are various. I talk about mobility, energy. I haven't talked to you about environment, but that is a big deal with climate change in our shoulders. And all these use information and communication technologies to do the recommendations later. Challenge. Let me talk to you about two challenges. I didn't go deep into the income, the difference in income. A big challenge I see is the price of houses. The use of a space in the city has to do where we live, where we work, how much we can pay. The classical model of urban economic is people that is optimizing, being the closest possible to the work with the amount of rent they can pay. Having more data science in this aspect is important, and why I'm showing here the different socioeconomic groups in LA. That type of things is hungry for more research, and I believe computer vision is revolutionizing this topic, because for me the next fun data revolution is through the images. So we have done some work here in KDD. Simple work at the beginning is you can have automatized way to see remote sensing data and convert that to land use. It applied well. I never had the feeling that I was really understanding the CNNs. Then I got a grant to work in environment. So if you see, next week is happening in Europe, climate change and AI. If you are interested in climate and computer science, I really recommend that conference, because it's perfect for deep learning algorithms, because you have different space, temporal, and data sources. You have human, climate, and environment. This is the motivational slide. In Beijing, in the same day at 2 p.m., in the same hour of the day, 2 p.m., you cannot see the building. That's called a haze event. And in the other days, you can see it like that. This is decreasing the quality of our cities. We really need to do something about air quality in general. And this is one topic I'm working. In this case of Beijing, there is 2 million people in a city, 5 million cars. It's a country city. And we only have 100,000 phone users. That's nothing. But still, we enter working in Beijing. The approaches is not doing, this is not, I'm not going to show you a result. This is, I'm introducing to you a challenge. Combining monitoring station data, satellite imagery, with the knowledge of networks in terms of mobility. What we're trying is to mix these things together to predict what we observe. One of the most dangerous components in the air is PM2.5. And then ideally, the right-hand side view, we can label the zones according to their land use, their environment, and all together work in healthier cities. That is the vision. Urban economics and climate change and AI. And to tell you an example, oops, this type of things, like these papers here, you can use Google Street Views, run the computer vision algorithms, and the result is that now depending where the people move, it's like you have the eyes in the street. I have the mobility, but now we have the images. Then we can do all sort of applications, because you are having eyes where the people move with the urban planning concept. I do not work in smart cars, like also have eyes. Computer vision for urban planning purposes. Then to conclude, I hope I convince you that ICT, meaning information communication technologies, data can be used to solve, to model and to do urban scale mobility models. Infrastructure demand, with infrastructure demand, we can plan traffic and foresee the introduction of new technologies and energy saving. That was the EV work. And clustering individuals and their social networks and how to use the space is key in recommendations for collective well-being. That summarizes what I talked to you today. With that, I have some minutes for questions. Thank you so much.
And thank you for that excellent and far-ranging talk. Let's give our speaker a virtual or physical round of applause. And let's open up the floor to questions. So you can either unmute yourself and speak, or if you'd prefer, you can also write in the chat and I will communicate your question. All right. Any volunteers? All right, I have a couple of questions. The first is a technical question. I missed exactly the relevance of the motifs in the first part of your talk. So I don't know what the significance of a motif would be in terms of urban mobility.
Are you familiar with the bio motif of Uri Allen? You're meaning by that, or the motif came like a nice way to validate, because the type of thing in excellent question, because to be fair, we didn't analyze it properly, the motif in itself. But in the motif paper, the first author is Schneider, it's an interface paper. It turns out if you ask how many graphs of 4 nodes you can have, is many more than the 5 significant motifs we observe in data. Yeah. The interesting part is that we need to have these motifs. We just had the fact that people would return home, that is a constraint, and sometimes they would put errands one after the other. That is what we call in human dynamic bursts of activity. Then just having the betas, that your probability to go to explorations, they come together, would produce a motif. Then in the motif paper, we compare travel diaries from Chicago and Boston with the model, and of course the phone data in there too. The motifs are the result of our circadian rhythm and these bursts of activity, and that everybody returned home. They came as a byproduct of the temporal model. And it's a curiosity, we didn't use it much. It's just that they are there. And it's powerful because if you ask 3 locations, 5 locations, the combinatoric gives you way more than what we observe in data. That's the aspect of the motifs.
I see.
Thank you for the question. Yeah, fair enough.
Before I monopolize our speaker, I'll ask if any of the other guests would like to ask a question. All right, in that case, I'll indulge myself. You mentioned deep learning from the computer vision perspective. Do you know of any work specifically in this type of complex systems for urban design that uses deep learning, hierarchical neural networks for at the level of network design or at the level of the actual dynamics, as opposed to extraction of features from images which are then used?
Wow, that would be super, super good. No, I don't. My question, I back you with a question. What Jure Leskovec is doing, I know he's combining Jure Leskovec from Stanford. He does GNN, and I think that is called graph neural network.
That's what I was thinking about, yeah.
Is this related to that? I need to study the work more in detail. But according to what my student described to me, he is using network properties to inform the algorithm, not yet into dynamic. What is interesting is, network structure appears first, then temporal networks. I believe Jure has been more into the network aspect of it, and the communities. He has a nice paper in which he used motifs to detect communities. But I don't know if he's going into the temporal yet, which is natural because first we learn the structure, then the motif, then come temporal. I think working in temporal network is something very useful. Keeping the story with network science is multiplex network. Networks interacted with network is what is up to date right now. Yes, the short answer is I don't know. The closest combining network and deep learning or hierarchical and neural networks would be, I would look at Jure Leskovec first. Who is citing him? Yes.
We have a question from the audience from Elizabeth, who says, thank you for this presentation. I'm interested in combining population and environment data to understand climate change impacts on population. That's where you ended your talk. I wondered if you could reflect on who you think is doing the best work in this field, particularly the use of big data to understand environmental shocks and human mobility. Thank you for your question, Elizabeth.
Yes, Elizabeth, I would recommend you. The beautiful thing is right now, climate change and AI. They're a group of students. What I love is that they belong. There is one student from ETH, Zurich, another from CMU. And there you would see, look at the speakers there, mostly look at the workshop. And what I most like is not only computer scientists. I was in the panel last year. You know who was in the panel last year? Jeff Dean, Jennifer Chase, people that are very recognized computer scientists, but they were not really climate change and AI. So it's not an easy answer, but if somewhere you would find the people working on this, would be in that workshop. Climate change and AI, they are an organization and they have workshops in Europe. The one running on December 12th, few days from now. Oh, yeah, this Friday, already we're finalizing this week, is the second. So it's the second edition in Europe of climate change and AI. And I also was there in AML, Applied Machine Learning Days in EPFL. It was great. So the European version of Europe, I call it EPFL, Applied Machine Learning Days, look into climate change and AI, and in Europe. And it's happening next week, and it have live streaming. Then you saw people working from cloud to fire, you name it. I could not identify one group or one person, but because they are PhD students, they really know how to see broad who is working on this. And they invite not the community of the advisor, they really see broad. Then that is something I keep my eye on. They even have a mailing list. I recommend that.
Okay, great. Any final thoughts or questions for our speaker? All right, in that case, let's give our speaker one last round of applause and say thank you very much for joining us today.
Of course, I wish you a restful end of the year. Hang in there. Take care.
You too. Thank you very much.
Very nice to meet you. Bye, guys.
Bye-bye.